Hello, everyone. Thank you for joining me today. My name is Ernesto Hernandez Hinojosa, and I am a PhD student at the University of Illinois at Chicago. And today I will be discussing part of my research on developing an optimal controller of a 5-link biped robot using quadratic polynomial model of a 2-point boundary value problem. So this next slide here is an outline of my presentation. I will begin with an introduction, then move on to background and related work, discuss the robot model, the simulator, the methods, the results, and finally the conclusion and the future work. So we know that for bipedal robots to get around, they must have proper control of the speed and foot placement at every step. It is difficult to control walking at every instance of the gait cycle, such as in between the steps, because most bipedal robots are underactuated. And to do so, you would need very strong motors at the ankle, and even then it wouldn't guarantee perfect actuation because the foot will begin to rotate when the torque at the ankle is too high. However, achieving control at the end of every step is easier to achieve, and this is known as a one-step deadbeat control. And this research, we worked with a 5-link planar robot model shown here in the picture. The robot has a total of 4 actuated degrees of freedom, 1 in each hip and 1 in each knee. The model has 1 degree of underactuation because the hip actuators can control either the position of both hips or the position of one hip and the torso, but not both hips and the torso simultaneously. One of the first demonstrations of step-to-step control was through the concept of passive dynamic walking. In the study, a walking frame that assimilated a human lower body was launched down a slope, and eventually it settled into a periodic gait with no control. And this idea has given rise to powered walkers that can transition into these cyclic gaits on flat ground using hip and ankle actuators. Some of these robots are listed here below. These robots are unstable instantaneously, but become stable over the time scale of a step. And this cyclic stability is known as orbital stability and is the primary means of balance in humans while we walk. One method of achieving this cyclic stability is by using nonlinear dynamics. Here, the nonlinear walking model can be linearized, and then using pole placement or discrete quadratic regulator can achieve control. And although this method is simple and quick, it limits the region of stability to a narrow region around the cyclic gait. Other methods used to achieve control over the cyclic gait are included here with some of their limitations. One method uses a nonlinear model, another uses a simplified model that maps to a nonlinear model. And finally, the hybrid zero-order dynamic model does control synthesis using a high-dimensional model. This is a summary of the method that we developed to achieve the periodic gait on the 5-link planar bipedal robot. In figure 1a, we use partial feedback linearization to reduce the dimension from a 10D Poincare map to 2D. Next, in figure 1b, we use the Poincare map for modeling the step-to-step dynamics, which further reduces the system dimension to a 1 dimension. And that dimension is the velocity of the stance leg. And next, we approximate the step-to-step dynamics using a quadratic polynomial model and estimate the region of validity using a support vector machine. And finally, we use a nonlinear programming to solve the resulting quadratically constrained quadratic program. And the novelty of our work is the use of a data-driven method to derive a quadratic polynomial model of the 2-point boundary value problem and identify the region of validity. Now, the model that we use, this is the model here is shown in this figure on the right. It's a 2D biped model. The physics parameters that we use were taken to resemble human anthropometric data. The state variables are the stance leg, X and Y positions shown here in the figure, and the 5 angles consisting of the torso angle, the left and right hips, and the left and right knee angles. 2 sets of equations are used to develop the simulator. One for the single stance phase, where one foot is on the ground, and the second for the foot strike phase, where the legs exchange roles. The first set of equations is formulated using Euler-Lagrange method and gives the equations of motion for the model. And we call these equations the single stance equations, shown here in equation number 2. And then the second set of equations are used in the transition to the foot strike phase, shown here in the figure, where the swing foot strikes the ground and becomes a stance foot. And at the same time, the previous stance foot applies an impulsive push-off, which is here IC1, along the leg, assuming the angular momentum and energy are conserved in this phase about the new contact point on the new stance leg C2, and integrating equation 1, we obtain equation 3, which are our foot strike equations in the simulator. Now the simulator consists of these 3 phases and 2 transitions. So we start the simulator in the single stance. We use single stance equations to integrate the system until foot strike. And then we move on to transition 1, which occurs when the swing foot C2 touches the ground. Phase 2 begins. We apply the foot strike condition, which was equation 3. We swap the legs. We move on to phase 3, where we use the single stance equations again to integrate until we're back in mid stance. And then transition occurs when the biped is in mid stance, and then the cycle repeats itself. Now, partial feedback linearization. So we had the simulator, and we moved on to implement the controller. So the states we chose to control are the swing leg, hip, torso orientation, and both knees. We use control partitioning or feedback linearization to perfectly balance the nonlinear terms. And after achieving partial feedback linearization, we implemented a PD controller whose goal was to track the reference acceleration, velocity, and position of the actuated joints. These are the equations we use to derive our controller. And in a nutshell, we use our equations of motion in the simulator to solve for the state data double dot. And then we use a selection matrix to eliminate the uncontrolled state. The equations for the control states is shown in equation 5. Equation 7 is the controller that has been linearized. And when equation 7 is plugged into equation 5, the nonlinear terms are gone, and we are left with theta c double dot is equal to our equation 6. And then to simulate the uncontrolled state, we use a selection matrix as shown in equation 8. So now we have the simulator and the controller for the actuated degrees of freedom, and the next step was to develop a method to control the humanoid's walking speed and step length. And we use a concept of a Poincare section and map, which maps an initial state of the Poincare section theta I and controls during the step ui to the state at the Poincare section at the next step, theta I plus 1. This map F describes the step-to-step dynamics, which is found by integrating the equations previously discussed from one mid-stance to the next. Equation 9 shows the Poincare map. I is the step number, theta is the state, which consists of theta and theta dot. U are the discrete controls that are set once per step, which are foot placement angle, as well as the impulsive push-off. F is the Poincare map that relates the state from one mid-stance to the following. The states can be further reduced by assuming that our partial feedback controller works as intended, and therefore the states now become theta and theta dot of the uncontrolled degree of freedom. And we choose a Poincare section to be at single stance, which is defined when theta 0 equals 0 and theta 1 is equal to 0. This means that theta 1 is known and the Poincare reduces to only 1 degree of freedom, theta 1 dot. And now we choose 2 control inputs to be the step angle and the foot strike. The step angle theta 2 is equal to alpha, and the push-off impulse at foot strike is equal to the I term. The Poincare map equation becomes this. So next, we want to predict the Poincare map so we can control the velocity of the humanoid at the Poincare section. And to do this, we generated data using a range of values for control inputs. And as outputs, we obtain the Poincare output as well as a feasibility flag, because for some inputs, the reaction would cause the model to lose balance and fall before taking the next step. and this was determined to be an infeasible solution. And then the feasible infeasible data set, this was used to find the boundary of the region. We used support vector machines for classification of the boundary problem. Using a linear kernel, we found the optimal hyperplane that splits the feasible and infeasible set, shown here in blue to be infeasible and red to be feasible. And we obtain a decision boundary plane that has a linear function. The equation of the hyperplane is shown here in equation 5, and this becomes our classifier equation. We tested with 125 samples and found an overall accuracy of 93.6%, predicting feasibility. Once we developed the feasibility classification model, we used the feasible set to develop a polynomial regression model of the Poincare map, shown here in equation 16. This is our Poincare map approximation of the feasible set. And so finally, we used the support vector machine decision boundary and the polynomial regression to develop a quadratically constrained quadratic program. The cost function is the squared error of the outputs in relation to their nominal states. Equation 18 is a polynomial regression equation in matrix format. This is our Poincare estimation. And m theta dot 1I is treated as a known constant because we know the state of theta 1 at the current step. And equation 19 contains the support vector machine classifier constraint. And these are some of the results that we obtained from velocity tracking. The plot on the top shows a reference velocity in blue and the track velocity in red. And then the plot on the bottom shows how our control inputs are changed to achieve the tracking, where our foot strike angle alpha is shown in blue and our impulsive push-off is shown in orange. The mean absolute error in tracking was about 0.0106 radians per second. And these optimizations took about 15 to 40 function evaluations, which demonstrate the feasibility for the real-time control. Now, for some applications, we simulated the walker walking over terrain with ditches. And we showed that the model can be used not only to track velocity, but also can modify the walking parameters to vary its step length. We used a system to simulate the walker walking over ditches using step length as a control input, as opposed to the step angle. The humanoid successfully varied the step length by controlling the impulse and the step angle. And we also used the approach on a compass walker climbing stairs, that's shown in the video here on the right. Now, the Poincare input for this model became 4-dimensional because we added an additional step height input. And we were able to classify the feasibility using a polynomial support vector machine kernel. And to conclude, we developed a controller approach that has a high accuracy and a quick solution time on a planar humanoid robot and achieves stability over a step. Our simple model covers a relatively extensive region around the cyclic gate, and it enables us to solve the 2-point boundary value problem in few iterations and function evaluations, enabling real-time control in the future. Future work for us will focus on applying this control paradigm on a biped robot on hardware. I would like to thank the RAM Lab at UIC, as well as my mentor and advisor, Dr. Bonsul, and Dr. Satichi for his help. And I would also like to thank the NSF for providing some of the funding for this work. Thank you for joining me today. I hope you continue to have a good conference, and I would gladly take any questions in the live sessions. Thanks again.